So I'll start with a small recap of last lecture and also some compliments. So okay, so last lecture I have introduced a diagram of schemes. So that I denote by E overline index A, and the indexing category is denoted by theta bar parenthesis. So this thing. And we have seen that this diagram can be used. So this can be used to give a new model of the spectrum omega that represent the RAM cohomology. So let me also remind you a little bit about how this diagram is constructed. So so theta bar in this notation is this is the free category having or admitting direct products. Or maybe the category admitting the direct product, freely generated by one object. Which I denote by E bar, and having so this object admitting with two arrows from the final object. All right, so this is that we think about them as the zero section and the section at infinity. Then this so omega itself also has a meaning. So this is omega is a presheaf on a category which I denote by Pn, which is the category of finite non-empty subsets of the integers. And so this so if I have I in Pn, this omega I is by so it's a subset of the set of differential forms, closed differential forms on the affine scheme AI, which is I will not define. This is given by, so it has coordinates indexed by the element of I, and they satisfy that their sum is equal to 1. So this is a subset. So this is exactly the subset of translate invariant forms. And I think I forgot last time to say that I want them to be defined over Q. So which are defined over Q. Okay. So it's actually a Q vector space of dimension the cardinality of I minus 1. Okay, so and then this theta bar omega n, this is by definition the integration over Pn of the functor omega, the functor theta bar omega. So maybe if I put, okay, so I will not maybe also write it down, but this is, so this is the category of consisting of families indexed by the set with value in object in theta bar, and this family is supposed to be the final object except for finitely many elements of omega I. Okay. Right. So somehow, yeah, an element of this category I will always denote this by, so it will be a couple I and alpha. And to this couple, so the functor which defines this diagram associate E alpha, maybe like this, Cartesian product with AI. So E alpha is really a family of finite set where the union is finite, and this is simply just the scheme E to the power E1 to the power alpha. Okay, so we also have seen that there is a natural foliation on this diagram. So how does it work? So essentially, so if I fix V in omega I, and we have this object EV. This is which is a family which is just point at E for at V, and then the final object everywhere else. Okay, so then the foliation on so EV times AI, which is just E1 times AI, is defined by so the foliation on is defined by, so maybe I write it like this, by thinking about the coordinates, or I don't know, if I write this as AI with a new variable, then we think about E as the exponential of the integral of V. Yes, and okay, so I want to explain it a bit, so to remind you a little bit more how we get this model of omega out of this diagram. Any questions? Sorry? Yeah, exponential. Maybe I should write exponential of. Okay. I mean, so what I mean by this, thinking about this, it means that we declare that D of E is V. Okay, so in omega the over E. Right, so I think I did not maybe explain this. in details last time. So let me do it now. So we define a pre-sheaf. So let's denote it by O tilde, maybe O delta omega on the category of smooth foliation over this diagram. Right, I will not okay, etc. As follows. So given I alpha and theta bar omega n, and given xf smooth, diff smooth over e bar alpha ai. So we do the following. We define O delta omega xf to be so by definition, this will be the O delta of xf, but what I modify the foliation on it. So I essentially I just take a fiber product with e bar alpha ai with itself, but where I put here the foliation. Okay, so is this clear what I mean by this? All right, so this has I put on this the coarse foliation, and so somehow this has the effect of taking some quotient of omega xf. Okay, so we somehow we endorse this with a finer foliation. Is this clear? Yeah. So for example, if I take here the identity, I get this guy here. So this has the effect to create more constant, right? So this guy is bigger than O delta of xf a priori. Okay, so what else I should say? Okay, so let me also introduce some notation. So we have this. We have morphism of sites. Again, I will not write down the category. So this is called rho. And this is called pi. Okay, and, so in particular, we have a direct image of sheaves along this morphism of sites. And then we have, with this session, I can now state the theorem that so there is a level-wise maybe, I don't know, let's say quasi-isomorphism between the following two things. So on one hand, we have this pi lower star. So like this. So we have this this construction that I explained last time, which I will not redo today. Then we apply this to pi lower star, rho lower star, and then we have the infinite suspension spectrum on that thing here, and maybe more precisely on O delta omega, but made fibrant, so CFT fibrant, and this is for the foliated topology, fibrant, and then this we make a tal fibrant before I apply this. So why I do this, because I am tensoring here with some power of the Tate motive, which has the effect that somehow which would destroy this property of being fibrant. So but I don't need to make it fibrant for the CFT topology. It's enough to do it for the étale topology. so then the quasi-isomorphism is between this and omega. And to be precise, I should maybe here one has to restrict to smooth foliation, but which are maybe let's say affine, maybe and also maybe Noetherian, and maybe some extra property, but this will not be very important for us. Okay. So, in fact, later, so I hope if I get to this at some point, later it will be somehow useful to work with a variant of this theorem, where in fact we replace this pre-sheaf by a smaller one, for which the same statement is true. So I just introduced this pre-sheaf today, so hopefully later we will see why this is somehow better than the other one. And the proof is again the same. So it's the same principle. Prove also that this theorem holds for a smaller pre-sheaf, which I will introduce now. So for later we need how to use smaller sheaf, which I denote by O tilde. So I just add a tilde to the previous notation. This will be here. So how this is constructed? So it's obtained as follows. So it's a little bit, so it's not as nice as the one I gave here. So I need to work a little bit to introduce this. So we do as follows. So again, we start with something which is smooth, diff smooth over one of these guys, E alpha AI. And so we look for the initial map from alpha to some alpha 0, surjective. So it makes sense to speak about surjective maps in this category theta bar. You can imagine what it means. So initial map like this, such that when I compose x to E bar alpha 0, this factors through the open stratum E alpha 0. Okay, so I look for the alpha 0, which is somehow largest among the all possible quotient with this property. Okay, then I do the following. So we look at, so we consider something that I think by A xf. So this will be a module with integrable connection. As this is my notation for the category of modules with integrable connections over E alpha 0, which is obtained which is the kernel of the following map. So you look at functions on X, and you have a derivation to which goes to omega x over f global section. But again, you somehow you modify your foliation here. And so how do you modify this? Again, maybe just making a fiber product with a coarse foliation. Yeah, I don't know. Or you can maybe denote it just like this. So if you want, this is the relative sheaf of differentials with respect to this map. Okay. So it's again you somehow you modify the foliation, you make it finer, so that you get more constant again, and it's not difficult to see that the kernel of this map is so it will be a module, it will be a coherent module over quasi-coherent over this guy, and it has a natural connection on it. Okay, so it's not very important, and it's not very difficult to prove this. So once you have this, then what you do, you look at, so next step you consider this guy, and you look at the smallest, or sorry, the largest. So it will be the largest, again, module with interval connection of logarithmic type. So again, what does it mean? So remember, we are working over this guy, which is just a product of copies of GM, right? And on this kind of on this, so it's a torus, and on this guy we have natural objects in this category, which somehow we can call them logarithmic sheaves, if you want. So they are obtained by adding formally a logarithm. Okay, so I will not maybe write it down. It's not so difficult. So it's just you are looking at section which satisfies the equation of a logarithm, differential equation of a logarithm. Okay, and this is the sub guy here. And then once you have this, then I think we're almost done. So we define O tilde delta omega of xf. So this is by definition, it will be the set of solution of this guy on the foliation E alpha 0 times AI, sorry, AI modulo of this E. So if I wouldn't do this step here, so if I put here just AXF, I would be just getting back this guy here. Okay, it's not difficult to see this. So you can the constant on this product, you can obtain them in two steps. First, doing so taking constant over the okay, like this, and then furthermore like this in two steps. But so what I did here, I replaced my A by something smaller, and so this is why we get a smaller presheaf. Okay, so this for the moment it's really not important. I just wanted to introduce this in case later I will use it. Okay. And so yeah, so the point is that the theorem is still true if you put a tilde here, and with the same proof. Okay, so this was the recapitulation I wanted to do. So today, so now I start with chapter 3. So maybe just before starting with chapter 3, just one final remark. Okay, so what we need to remember for what will come is the following statements, which would follow directly from the theorem. So for later, we need to know the following. So we need to remember just one thing, namely the existence of a map, which is of course up to quasi-isomorphism, and the map would goes from the thing that we are interested in, the RAM cohomology, to this gadget dot n theta. And so instead of putting Feynman replacement here, I will do it just directly here and for the FT topology. Right, so we only need to know that there is such a map, and of course it's a map of algebra, so it cannot be 0. All right, so this is what we need to remember. Now I can start with chapter 3, and I think the title is so it will be about foliated motifs. And so before I start with this chapter, I want to tell you what is the goal of this chapter. So what do we want to do here? So the goal. So yeah. So I mean, we have this map, and somehow what we are trying to do is remember, we want to compute this homotopy limit of the Church complex of this, and the idea is somehow to work rather with this model of omega. But this is still not good enough for what you want to do, and so we still need to do to somehow to replace it by something kind of smaller or maybe more cofibrant. And so this is one step in this direction will be made in this chapter. And so the objective in this chapter is to do the following. So here the goal is to replace. Maybe let's give a name to this map here. So to replace in star. So on one hand, so we want to replace this part. So maybe I don't write it. I want to replace this by the following variant, so which a priori maybe look a bit more complicated, but at the end it will be really a crucial improvement to the statement. So what we want to do, we want to replace this part by the following thing. So we will do again so direct image along the map rho, but now instead of taking fibrant replacement for the foliated topology, I'll take just for the Nisnevich topology, the Psi-Nisnevich topology. So I replace this spectrum by something which is fibrant for this topology. I apply direct image, and then again I do another replacement, which is now the FT fibrant. Okay, so clearly there is a map from this part here to this part here. And somehow the goal will be to show that this map is essentially an isomorphism or quasi-isomorphism or equivalence. Okay? All right, so this is somehow the goal. of this chapter. And so this is obtained. So this is obtained by using the so-called motivic Grothendieck Verdi duality. So which is part of the sixth operation formalism. And this will be in the context of foliated motives. And so I need to quickly somehow remind you how we can speak about motives in the context of foliation, and how do we get this Grothendieck-Verdi duality, and then how we use it to prove this improvement, to get this improvement. Yes?
In this theorem, we were somehow taking an étale fiber replacement of this thing. And that's no longer the case.
Yeah, so somehow it's, so because I take, okay, so in the theorem there was a parenthesis here,
Yeah.
and then a parenthesis here, and then there was étale fibration. So I claim that this thing here received the one from the theorem. And the reason is that, when you make this guy fibrant for this topology, you can do it in two steps. You can first make this fibrant for this topology, apply this functor, and then make it again fibrant for this topology. And it's exactly the same. But then if you write it like this, then it becomes clear what I've said, because the étale topology is coarser than this topology. So this is étale fibrant also. Okay. Yes?
Clear that this goal is a priori related to the duality.
What is clear? Sorry.
I think I question: why is this related to duality? This goal?
Why this goal has to do with duality? No, it's not clear. So you will see this later. So yeah, I'll use this as an ingredient to prove this, but it's not a priori clear why this has to do with it. Okay, so I want to start by recalling quickly the formalism of the six operations in the motivic setting. So this is a classical stuff, but maybe I assume that you're not familiar with this, so I try to recall this, but quickly. Okay, so it will be somehow important for what I want to do to work first in an abstract setting, because I might need to apply this different situation. So we start with So we start with an abstract. Start with abstract setting and make a definition. Okay. So we fix. So let's fix scheme S, and denote by scheme over S. So this will be the category of quasi-projective S schemes. So I restrict just for simplicity to quasi-projective S schemes. So and quasi-projective mean in particular that I want my scheme to be of finite presentation also. And so I consider. So we make a definition. So a homotopic stable homotopical two-functor over S is a two-functor, contravariant. That goes from, so it's denoted by H, goes from quasi-projective S schemes to the two categories of triangulated categories, and sends a map of schemes to a functor F star upper star from Hx to Hy. And so this has to satisfy some properties, so satisfying the following list of axioms. All right, so here are the axioms. So are rather, I'm sure you have seen these kinds of things before. So first one is we want that, this is a bit silly, we want that the category of at the empty scheme to be trivial, that's 0. Then we want that for every F upper star has a right adjoint. That, of course, we denote by F upper star. And if I is an immersion, so locally closed immersion, we want that the co-unit map to be an isomorphism. Then third property, let's see which one. Yeah, so if F is smooth we ask that f upper star has also a left adjoint, which denoted by f lower sharp. And moreover, given a Cartesian square like this, so let's call this maybe f g f prime g prime, and let's ask so such that f is smooth as before. So then in this case we want that f lower sharp g upper star, which receive a natural map from f upper sharp f lower sharp g prime upper star, is an iso. Okay, so then axiom 4 is that so if you have E and G, so E a closed immersion, and G the complementary open immersion, and then we want that the pair I upper star G upper star to be conservative. Then the last two are as follows. So 5 and 6. So 5, let's denote by P projection from an affine line over X to X. Then we want that or for example, we could ask that the identity map, the co-unit map, so the unit map is an iso. And the last one, so this is called, of course, A1 invariance. This is called stability. And this is so we consider also the zero section. And then so here we ask that the functor P lower sharp S lower star is an equivalence of category. Okay, so let me make a remark about this. So as I said, so of course, so these axioms are part of the package of the 6 operations. So you might ask, why do I bother by listing these axioms? So the point is that the point of listing those axioms is that they are somehow they follow easily from the construction of categories of motives. And furthermore, so it was realized by Voevodsky that these axioms are also sufficient to imply, in fact, the full package of the 6 operation. So, these are sufficient to derive the full formalism of the 6 operation. Okay, so as I said, I will not need to have the full formalism for what I want to do, but what I need is somehow what comes at the end of developing this formalism. So I will quickly somehow go into how one obtain this full formalism out of these axioms. Okay, so let me maybe state this. So theorem. So I state this in an informal way, maybe. So informally. So one can, given each as above, one can define functors f lower Schräg, f upper Schräg, satisfying the usual properties. Yeah, and I should maybe say that. I mean, I'm speaking about the 6th formalism, actually, but actually I'm only speaking about four of the 6 functor. So there's also the tensor product in the internal home, which I will skip today. Okay, so I mean, of course, this will not follow from the definition. You need to add this as an extra data. Okay, so yeah, I want to sketch the proof of this, and then tell you what I need exactly later on. Okay, so sketch. Maybe better to say a sketch of the construction. So take some place. Okay, so maybe the first step would be as follow in the construction is to define I upper shrink for a closed immersion. This is quite easy, so make a definition. So if you have, it's called C inside X, closed immersion, and you have an object over X, so you define I upper shrink of M as follows. So you define this by saying this is I upper star of the cone going from M to G lower star, G upper star of M, maybe shifted by -1. Where, of course, where G is a complementary open immersion. And so an easy exercise to show that this is well defined. So this defines a triangulated functor which is in fact a right adjoint to I lower star. And so by construction, one get this familiar exact triangle. And in fact, so by setting G lower shrink to be G lower sharp, which we know that it exists. So this is the left adjoint to G upper star. We also get a distinguished triangle which is kind of dual to this, namely G lower shrink, G upper star, and I lower star, I upper star, M. And so these are called the localization triangles, exact triangles. So this is somehow the first step, is to see that one can do this out of the axiom, and this is quite easy. Let's try to put this here. So the second step is to somehow to define the so-called Thom equivalences. And this is done as follows. So you start with X scheme for S, then you take M locally free of finite rank or X module, and then you define Thom of M to be P lower sharp, S lower star, and similarly the inverse Thom equivalence to be S upper sharp, P lower star, P upper star, sorry, where P is the projection of the vector bundle set to M, and S the zero section. And so it follows easily from axiom 6, and maybe with this localization triangle, that these are indeed equivalences of categories and that they are inverses of each other. Okay. So should maybe say this maybe orally. So in many familiar contexts, these functors they are actually given by Tate twist. So let me make a remark. So in many situations, for example, say maybe for electric sheaves, etc. These equivalences, so the thumb space, thumb equivalence to M, these are given by, so there is an isomorphism with the thumb space of a free module of the same rank. And which is usually, and this guy is usually denoted by a Tate twist, something like this. So if R is a rank, this would correspond to this. And so typically this is the case. Let's say, for example, if you are working with rational coefficient and etal locally. So if you have a topology which is finer than the etal topology and you are working with rational coefficient, it's you can prove you can construct such isomorphism. But somehow it's not important for us, and it's actually more canonical somehow to keep this this functor here. Okay, so then so an important fact, which I will not maybe prove, but it's not so difficult. It's just it requires some time to do this. So is that if you have so if you assume that X is, so let's X is smooth, let's say over S. There are variants of this, but let me just state the simplest one. So we take X smooth over S, and Y. Sorry, maybe. So X and Z smooth over S, and you take a closed immersion. Okay, then okay, so a closed immersion, and okay, I want this. Okay, let's say we are over S, and then let's call this P and Q. Okay, let's take anything, just make it more general. So we take this situation. So T will be smooth, will be a scheme over S, and take this diagram, and assuming that P and Q are smooth, this is closed immersion. Then if I do this, S upper shake, P upper star, then this is isomorphic to Q upper star and I think Tom space the normal bundle of S minus 1. So this is called purity. And so it's kind of an important ingredient in constructing these functor f upper Schrick and f lower Schrick. Okay, so somehow this is the fact which say that the next definition is reasonable. Reasonable in the sense independent of choices. All right, so here's construction. So the construction of f upper Schrick, f lower Schrick. So it's done in 2 steps. So first we assume that f is smooth, and then we define the following. So we said that, so we define f upper Schrick by definition to be the Thumb space of the sheaf of Keller differential composed with f upper star. And dually, we take f upper Schrick, f lower Schrick to be f lower sharp composed with the Thumb equivalence minus 1 omega f. Okay, so clearly this is a left adjoint, so this is left to this, which is good somehow. We want to have this adjunction. And then in general, so for a general f, we factor f as follows. So let's say that f is going from y to x. So then you factor it through v such that this is a closed immersion and this is smooth. Let's call this P, let's call this S. And then you set that f upper Schrick is S upper Schrick, P upper Schrick. So both things make sense now, right? And similarly, f lower Schrick, this is S lower, this is P lower Schrick, S lower Schrick. I don't know, I don't remember if I said it or not, but S lower Schrick, but by definition S lower star. Okay, and then somehow then use this fact, use the previous fact to show that this is independent. This is independent of choices. Okay, and then Also, it follows from this construction that given, so maybe like fact, so given a Cartesian square f prime g prime, we have so-called exchange or base change isomorphism as follows. So f lower star g upper shriek is the same as f prime lower star g prime upper shriek, and similarly g upper star f lower shriek is the same as f prime lower shriek g prime upper star. Okay, so of course important is Cartesian square. So this follow essentially from axiom, remember 3 maybe, axiom 3, which was saying something similar, something like this, when f was smooth and for the f lower sharp, and since f lower shriek is essentially f lower sharp, in the case of smooth map, then this is kind of clear if f is smooth. And in general, one decomposes the problem into 2 parts: closed immersion and smooth one. And the case of a closed immersion is usually an easy consequence of axiom 4, maybe the thing that the locality axiom. Okay, so this is kind of easy consequence of the axioms. Okay, so now we come to the point that I need. Which is this variant of, this is that can be called maybe the Grothendieck-Verdier motivic duality. Yes. Yeah, I mean, I am okay. I assume that my scheme were quasi-projective from the beginning. Otherwise, you can just take the maps that you can factor like this, and then there are techniques to glue and so on. I mean, it's just not important for what I want to do. Yeah? Sorry. Which purity? What do you mean? The thing that I erased. Yeah. This isomorphism between p upper star s lower s upper shriek is the thumb space. This is the consequence of. It's essentially I mean, you construct this using the so-called deformation to the normal cone and some. It's maybe not. I mean, it's not completely direct, but it's I mean, I mean, there's also a purity for in a more general setting. For example, if you take a regular immersion of scheme over Z, then this will not follow from the axioms. It follows when you are smooth over a base. Yeah? Okay, so so as I said, somehow the most important fact for us is the following theorem, which we can call it the Grothendieck-Verdier duality. Let's say the following. So, so given f y to x, quasi-projective maybe, that exists natural transformation f flower shriek to f flower star. Let's call it maybe usually called alpha. Such that when it satisfies a bunch of nice properties that will not state, compatibility with composition and so on. But the important thing is such that if f is projective or proper, f is projective, then alpha is an isomorphism. Okay, so the natural transformation, which is an isomorphism when f is projective. Okay, so I want to sketch the proof of this. So it's not a difficult proof. So, but there is one place which is somehow kind of a bit magical, which I think. I don't really understand what's going on at this point. Also, I can follow the argument, but it's somehow it's a proof that does not really tell you what's happening in some sense. But I will try to give a detailed sketch of the proof of this theorem. So let's first construct this map. So let's first construct alpha, and this follows essentially from what we have already. So we consider the following diagram. So y, x, y, and you take a fiber product, and then you have the diagonal. So of course, my schemes are separated. So this is a closed immersion. This is identity. This is f, p1, p2, and this is Cartesian. Okay, so we start with this diagram, and then we do the following. So we want to go from f lower shriek to f lower star, and so we do as follows. So we write this as follows. We write this as f lower shriek p1 lower star, diagonal lower star. So since taking this as a same identity, we have this equality. And then we do, so this is an exchange transformation, which somehow exchange these two things. And we can go to f lower star, p2 lower shriek, delta lower star, but delta lower star is also delta lower shriek, so I can put a shriek here, and this is f lower star. So I did not really speak about this kind of transformation, but somehow it follows by adjunction from maybe. So yeah, we know how to. So there is identification of going going by shriek star shriek, and by using adjunction one can deduce such a map. If you want, I can do it for you, but it's. Okay, so this is how the map is constructed. It doesn't really tell you much about it, but it is a fact that somehow this is. In realization, you have also this kind of map, and this is really, you can think about it as cohomology with support mapping to cohomology without support, and one can show that this is compatible with the one I constructed in this way. Okay, so the point is to show that when f is projective, that this map is indeed an isomorphism. So this is what we want to do. All right, so okay, so as I said, we now assume that f is projective, and you want to show that alpha is an isomorphism. And so there is so it's clear that it is clear that this is true for a closed immersion. If you look again at this diagram, when you have closed immersion, then P1 and P2 are this closed immersion. Okay, so nothing to prove. The claim to prove is somehow stable by composition. Okay, and so we end up. So we need to do the case of the projective of the projection of Pn. So maybe X. Okay, so we reduce to treat this case. And also, so there is kind of an easy lemma. I mean, easy in the sense that nothing very surprising happening here, and, which would tell us that in fact the natural transformation that we are looking at is indeed an isomorphism if we precompose by P upper star. And also, similarly, if we precompose by P upper shrink. So I will not prove this lemma. It's I think it's not so surprising, and I think one can believe that this is true because I mean, at the end, so for instance, I mean, this guy here is essentially the motive of Pn, and the motive of Pn. So it's a cellular variety. So you have this covered by affine spaces. So it's not so surprising that you can do this. And in fact, this is it's a nice exercise to try to do it yourself. Maybe it's using the axiom, like using namely homotopy invariance and localization to prove something like this. Okay, so I will not do it. It's really, I mean, it's actually harder maybe than what I want to do now, but somehow it's not surprising, I think. So I don't want to do it. But so somehow the surprise is that this lemma is enough to conclude. And this is somehow what I said, that I mean, I can follow the argument, but I don't understand what's happening. So what I'm saying is, if you know this, that these two things are isomorphism, then you can show what you want. And this is a formal argument using just playing with adjunction. And I want to do it for you. So here's how it works. So we use this isomorphism to define. We use this iso to define maps in the opposite in the backward direction. So we can go from P lower star to P lower shake. In fact, in two ways that you can imagine what you do. So you can. So we have the unit of the adjunction between P lower upper shake and P lower shake. Then we have this isomorphism. Right, and then you can. So this is co-unit. So unit, and you have the co-unit. It goes like this. So let's call this beta lower shake, and similarly we have beta lower star, which is defined like this. So again, use. All right, so we have these two maps, and so claim beta lower star, beta lower shake are, I think, left or right, I don't know, right, then left, or left then right, inverses of alpha. And I can even maybe even do this for you, so at least one case. I mean, so maybe before this, I mean, I just want to stress why do I find this argument a bit surprising? I mean, you see, what we know is that so you have the direct image or the extraordinary direct image of the constant motive of P upper star, which is something constant, which is not so interesting. And we know that when we apply this transformation to something constant, we get, or locally constant, we do get an isomorphism. And we are deducing from this that it's also the case for any kind of sheaf you have on Pn. Right? So Pn is very big, so you can put any variety, for instance, in it. Take a constant sheaf on this variety, and then you can apply to it, and it's still true. So this is why I find this argument a bit surprising, and somehow does not really is not really telling us what's happening. Okay, so. So as I said, I want to prove that one of the two compositions is identity. So let me just see which one I should take. So I'll take beta lower star composed with alpha. So this is going from so this is alpha, this is beta. So actually, what I will use is that yeah. So I want to show that is this correct? Yeah. Yeah, I think I took the maybe Let's try this one. I'm not sure which one will work, but okay. So we want to show that this composition is identity. So is identity, and we do this by looking at. So we look at the thing that we get by adjunction. And we try to show that this thing here is an isomorph, is identity. But then how do we get this from here? We get it as follows. So we go from P upper star to P lower star, P upper star, P lower star. We apply, sorry. Okay, so here, this is the co-unit here. And then we apply our natural transformation this, and then we apply co-unit. And we see, so to be able to conclude, it's enough to show that this map is identity. But this map is what is, so this is this map on which I applied on P upper star. And if I go back to the way this is defined, you see, if I put a P upper star here, I do get the inverse of the map I started with. Okay, so the point is that B lower star, P upper star is indeed the inverse of alpha P upper star by construction. Okay, and so this gives us what we want. All right, so I think this is enough for this proof. So let's go to the next paragraph. This will be categories of foliated motifs. Okay, so here I want to just quickly remind you how we can construct a category of motifs out of any space, and in particular out of foliation. So I'll do quickly review quickly the construction, just to fix some notation. And okay, so we fix. Let's fix foliation. So maybe singular. Okay, foliation, and this will be the base of the foliation that I will be considering. We fix also T a topology on foliation. So for the construction, it really doesn't matter what you take. So, but somehow the natural choices and what I will have to do later is to take tau among the following choices. So you can take the Psini-Snevich topology, Psi et al, Psi foliated, or the foliated topology. So these are natural choices of topologies to take. Now the most important for us today will be probably this one here. So and let's also fix lambda would be the coefficient ring that I can take lambda to be Q, K, and in general we assume always implicitly that it contains the rationals. Okay, so here's the definition. So so the category of complexes, presheaves on smooth foliation and lambda has a projective A1 tau local structure, model structure. And so we set, so for the A effective tau S E and lambda, but I will tend to maybe not to write lambda anymore. This is the homotopy category of this model structure. Okay, so this is so object of this category are called object of this are called foliated motifs. One should not take this this terminology too much seriously. There are probably better definitions of what a foliated motif should be. Just a convenient terminology for us. And so if I have xf diff smooth over C, we associate to this its motive, its effective motive. I should say maybe they're called effective. Maybe effective. And this is, by definition, this is just the free sheaf on XF, which I think about it as an object in this category. And of course, we need the stable version of this. I should maybe say here, I mean, maybe it's clear, but of course, I mean, there are choices. You could think about A1. I mean, you have to choose a foliation on A1, and of course, we will take the coarse foliation here. Okay, as usual, we think about smooth varieties as foliation, and those with the coarse structure. And similarly for T, so here, as usual, we denote by T, A1 pointed, E1 pointed by 1, free sheaf on it. And so we need to, so this is the date motive, we need to tensor invert T, and okay, we do it as usual, so let me just write it down just to be sure that there is no confusion. Okay, so one just repeat the previous definition. So, okay, the category spectra may be symmetric. I don't know if you T spectra, complexes, presheaves, smooth foliation, ES, has a stable A1 tau local model structure, and we set for the A tau SE lambda to be the homotopy category. And similarly, so the object here will be called foliated motive without effective, right? So objects are called foliated motives, and if you have a particular diff smooth foliation over SE, you can associate to this its motive, and this is denoted by like this, and this is, of course, the infinite suspension spectrum of the free presheaf on XF. Okay. So these are the categories of foliated motives, and now we want to see if they satisfy, if they have this formalism of 6 operation. Okay, and so, yeah. Let's see. We have the following proposal. So, as I said, somehow most of these axiom of a stable homotopical two-functor, they follow from the construction. And in fact, all of them except axiom 4 does not. And so it's the same story here. So I'll just repeat it. So a proposition, the two-functor that takes a foliation into this category of fol PA. So we can look at the effective and the non-effective. It's actually, so I put it into parentheses so that I'm considering both version. So this two-functor satisfies the obvious analog of the axioms 1 to 6 of the definition of a stable homotopical two-functor, except maybe the following one. So there are three exceptions, which is maybe too much out of 6, but so the first exception is that is the second half of axiom 2. If you remember, this is the fact that the counit of the adjunction I upper star, I lower star for a closed immersion, or for an immersion, that this map is an isomorphism. This is not obvious. Axiom 4 is also not obvious, and axiom 6. And in fact, axiom 6 is not true for the non-effective version, for the effective version, but in fact it follows from the other axioms in the stable version. So in the stable version, so maybe moreover, in the stable version. Axiom 6 follows from the others. In fact, yeah, so if you know these two axioms, actually, we can prove axiom 6. Okay, so I'll sketch the proof of this. It's really direct from the construction, but just it's maybe good if you haven't seen this before to see it once. So I'll not give the details. I'll just maybe point out what are the ingredients to get each axiom. Axiom 1 is, I think, we don't need to speak about it, right? Axiom 2. So yeah, this is a sketch. So first half of axiom 2. This is just existence of right adjoints to F upper star. This is really this is obtained from the adjunction F upper star, F lower star on the level of presheaves by deriving, by extending to spectra and so on. And more precisely, so we have this this morphism, or maybe it's not really a morphism of psi, but we can pretend that it is a morphism of psi. So let's say F S prime E prime to SE. So we have this morphism of psi which is given by pullback, right? So if you have an object here, you pull it back, you get an object here. And so this is called F. And whenever you have a morphism of psi, you have an adjunction, F upper star, F lower star. And this is, you take this one, and then you extend it along the construction, and you get the adjunction on the level of category of motives. Yeah? Then second is axiom 3. Axiom 3 is again, it's the same story. So it's about F upper star having a left adjoint. And again, this is obtained by a left adjoint on the level of presheaves. And here the point is that if F is smooth, so if F is diff smooth, then you also have another functor, let's call it F lower sharp, that goes from smooth foliation. So now I have to go this. So it goes in the other direction. So when I write, I mean, really the functor goes backward, right? So it takes a diff smooth foliation over here and send it to itself. But of course you now, so here this guy was over S prime E prime, and here it's over S E. Okay, is this clear? So this exists because F is smooth. And one can show that, so this also gives a morphism of sight, if you want, and it has also an adjunction, and it turns out that the inverse image, so we have this adjunction, and it turns out that the direct image is actually F upper star, and this gives the left adjoint. Okay, it's simply the fact that when F is diff smooth, the inverse image functor is actually very easy. It's just restriction along this functor. And this also, so there's another part in axiom 3, which is this Cartesian square. Let me write it down. Okay, I mean, just put it like this. So this was F. And we want to show that, remember, we want to show that F sharp, G upper star is the same as F. Okay, so we want to show this. And to do this, so what we do, so we evaluate this natural transformation on something. So I start with some guy here. So I can take the motive of something. So it's enough to check this for representable. So I choose the motive of a foliation, and I try to see what happened if I evaluate this. Now the point is that in this particular case, if you apply F lower sharp to this guy, what do you get? You get again the same thing, the motive of XF, but now considered as a foliation over this point. Okay, and now and then taking inverse image is what is just the motive of the base change. Okay, so forgetting base change, and then or base change forgetting, and I want to show that it is the same thing, and then this is the usual property of fiber product. Okay. Okay, so next thing is axiom 5. And remember, axiom 4 is a bit harder. So, but what follows immediately is, for instance, axiom 5. So this is just a direct consequence of homotopy invariance. So since we imposed homotopy invariant, it's not so surprising that we get it. But let me just do maybe the proof. One way to do this is as follow. In fact, it's just a reason to say this maybe important fact. So if you have P like this, which is diff smooth, then the functor P lower sharp, P upper star P lower sharp of something has a nice, you can think about it as nicely as follows. It's actually just some kind of a tensor product with M. Right, so if M is indeed a complex of presheaves, then when you do this, P upper star P lower sharp is just tensoring with S prime over E prime. Okay, so this is a general fact, and so in the case, so if P is a projection of an affine line S, then this axiom becomes clear because we know that the affine line is contractible by construction. Okay. Okay. Now, last thing is axiom 6, and this is in the stable setting. We have to invert the Tate motive, otherwise this has no chance to be true. Stable setting, and assuming the localization property. So how do we prove this? So remember, we want to show that this is an equivalence. But using localization, we can write this as follows. Okay. So let's fix an object M in so a foliated motive. Over the, yeah, maybe I take some notation. So this is over, let's see. Then, so we have the following distinguished triangle: P upper star, S lower star, M, and here we have G lower star, G lower shriek, yeah, G upper star, P upper star, whatever, something like this, a distinguished triangle. And so if I apply to this P lower sharp, so this is sharp, sorry, we get this. Okay, now this guy is, we have seen this is simply M because P is a projection to the affine space, and this is, and this is by the same formula here. This is tensoring with the this is tensoring with GM. Okay, and then so this means that this is the same as tensoring with T. In fact, T shifted by 1. Okay, and since we inverted T, then this is an equivalence. Okay. So okay, so now we come to the third paragraph, which is localization axiom. Okay, so we want to see how I mean, if the remaining axiom is also true, namely axiom 4 and the second half of axiom 2 in the context of foliation. In fact, it won't be. I mean, yeah, one has to put some restriction for this to be true. So maybe let's see. Maybe it's time to take a break now. 15 minutes a break, and then we continue. Okay, so you just wanted, so I asked me about this exchange. So if you have a Cartesian square like this, so we want a map that goes from this to let's just shrink. Okay, so we want to define this map. This is the exchange morphism of this type, lower star and lower shrink. And so, yeah, I think there are, as usual, there are two ways to get this. So here's one way, and they are the same. Here's one way, would be probably this. So you take the unit, and you apply this to f prime upper shrink, f prime lower shrink. Okay, so you start with an object here, and you are applying this functor. So what you do, you first do it like this. Yeah, and you take the unit of this adjunction here. Okay, and then you have this exchange isomorphism between upper shrink and lower star, which is an isomorphism, so it doesn't write it. So I suppose this would be this. Right, and then you use the co-unit here. All right, so I wanted, now I want to discuss the localization axiom. For foliated motives. Okay, so I state the theorem, and then explain a word which appears in the theorem, and then maybe sort of explain the proof later. All right, so here we have to, so it's important to choose the topology the right way. So in fact, it's enough that the topology is finer than the Cini-Slivich topology. So for example, if you take the Slivich topology, this theorem will not be true. Okay, so what do we have? So we take, so we fix some notation. So we take a diff smooth foliation, and you take a closed immersion, but not any closed immersion. You have to assume this closed immersion to be admissible, and I'll explain later what do I mean by this. So closed immersion and admissible. Okay, then we have what we expect. So okay, so there are three properties, which are, so the fact that the pair E upper star, G upper star is conservative. Of course, G is complementary open immersion. So conservative on foliated motives. Then for every foliated motives, so for it can be effective or not, it doesn't matter, for the topology tau. We have a distinguished triangle. Again, as expected. So. And also the property which is the second half of axiom 2, namely that I upper star, I lower star identity is an ISO. Okay. Right. So I need to tell you what is an admissible closed immersion. And so before this, I need to introduce the notion of special and pre-special closed immersion. So make some definition. Okay, so pre-special closed immersion this is a basic closed immersion, which means that the defoliation structure on Z is induced from that on X, whose ideal I of definition satisfies the following properties. So there are three properties. First, we ask this ideal to be locally cyclic. Which means that it's locally generated by one element. It does not need to be locally principal, but it's locally cyclic. The ideal I over I square is locally free of rank 1 on Z. And the last property is that we have, or the complex Z I over I square going to inverse image of the sheaf of differentials on X to that on Z to 0. So this is, I have this complex. So this is an exact sequence which is locally split. And so it's like a version of notion of a regular immersion for dimension 1. Okay. I have some space here. So, and moreover, so if yes, it's generated by one element. So cyclic is like, so a cyclic module is generated by one element, like R mod something. Yeah. So yeah. So generated by one element locally. No. No, I mean, so if, no, I mean, R mod an ideal is locally cyclic, but not principal. Okay, I mean, no, I mean, a principal idea is like it's a free module of rank 1. I'm asking just that it is a quotient of a free modulo. It has one generator. And in fact, yes. So if I is locally principal, we say that I is special. Okay. Is this clear? And I have some space here, so I can say also what is admissible. So we say, so a closed immersion is admissible if it is locally a composition of pre-special immersion. Okay? Okay, so for instance, any regular immersion between smooth schemes will be admissible. So I'll tell you very soon why. I mean, yeah, it's of course it's maybe a bit weird to ask I to be simply locally cyclic instead of locally principal, but there is a good reason for this, and so I'll explain this very soon. So somehow the notion of pre-special has better stability properties than the special. And maybe just a small remark here is that, so remark, just clear. So if xf is diff smooth I pre-special, then of course then zf is also is diff smooth. And even more, so the rank is the rank of omega xf minus 1. Right, so in some sense, the dimension drops by 1. This is clear. So, yeah, the reason why we prefer somehow the pre-special closed immersion is because of the following lemma. So let I be a pre-special closed immersion let x prime f prime be a diff smooth XF foliation and let I prime be the base change I, then I prime is pre-special. All right, so said differently, pre-special closed immersion are stable by base change along diff smooth maps. And remark, this is wrong for for special immersion. And maybe I leave it to you to find a counterexample. But we will see actually that the difference between pre-special and special is actually not so big. This will come. This will be the next level. Okay, so let me give the proof of this. So, so let I prime be the ideal of the immersion E prime. So, things that you generate by I. So, so since this is locally cyclic, then also I prime is locally cyclic. Cyclic, which implies then that I prime over I prime square is also locally cyclic. And furthermore, we still have this exact sequence. Except that we don't know anymore that it is exact on the left. But yeah, but what we know that so this is I prime. We know that this map here is actually the inverse image of the similar map for I. Right, plus the identity, so direct sum, the identity of some locally free O module. Identity or isomorphism. Why this? This is because of the assumption that X prime F prime is diff smooth over XF. Okay, so this. And so in particular, this implies that the kernel. So let's give names to these guys, A, B. So the kernel of B is locally free of rank 1. Right, since we know this, that it's the case for this map. Right, but now then we have that. So A is a surjection, so induces a surjection of a locally cyclic to a locally free, locally cyclic to a locally principal, to a locally free of rank 1, hence induces an isomorphism to the kernel of P. Okay? So this is the proof. Okay, so yeah, as I said, the difference between special and pre-special is not so important. In fact, we have the following lemma. So if we assume that we have a pre-special closed immersion. And so then if xf is diffless, smooth and reduced, then I is special. Okay, so again, okay, so right. So what do we need to do here? We need to show that I is locally principal, not only locally cyclic. Okay, so and this is a local question. Local question. So we may assume that that I is cyclic, so it's generated by one element, global section. Yes. We know that. Remember, we also have this exact sequence. And so the class of A goes to the class of DFA. And so by hypothesis, we know that DFA generate, so it spans a locally free module here, which is also a direct sum, locally a direct sum. Okay, so we can assume that, so by working locally, so working locally, and maybe replacing x by a neighborhood of z, we may assume that actually dfa, not only its class here, but that dfa in omega xf also spans a direct sum on of rank 1, and even free isomorphic. Yeah, certainly free. Okay. All right. So then this means that so from this I know that I can find a surjection, let's call it rho, which would send dfa to 1. Okay, so this can be achieved by working locally and using the hypothesis. So now we are almost done. So such a map, this map rho give us a derivation, right, which is simply rho composed with df from Ox to itself. Such that applied to A, it gives us 1. Okay, and remember what is our goal? Our goal is to show that that I is principal, which is so the same as saying that A does not divide 0. Does not. This is what we want to show. Right, so we use this fact to prove this. So assume that we have this equation, A times B equals 0 for some B in Ox. We want to show that B is equal to 0. So we apply the derivation to this equation, and you get that B is equal to minus A delta B. All right, and then this means that B squared is equal to B, but this is 0 since AB is equal to 0. Now we use the fact that X is reduced, so X reduced implies that B is 0 as we want. Okay. Still one fact about these special immersions. So we have somehow, of course, special are better than pre-special, and this is because of the following fact. So if we have closed immersion, which is special, assuming that X affine and the ideal is principal, not only locally principal, okay, then there exists a diff étal morphism U from this power series thing to XF. Of course, such extending E, and such that the parameter T is equal to A composed with U. And moreover, this induces an iso between T, F, and the weak completion of X along C. Right, and this is actually a particular case of something we have seen before. So this is a particular case of a proposition about weak completion in some situation which implies that we have something like this. Okay. So I did not give numbers to propositions, so I will tell you which one. So. All right, so now we can start the proof of this theorem, of the localization theorem. So okay, so I proved just the main case somehow of the theorem. So concentrate on the main case, which is we assume that I is pre-special. We work, and also we work in the effective setting. So the way that we go from effective to stable is kind of standard and not so interesting. So. All right, so yeah, before I start, I need a funny definition. I think we have, I spoke about this actually, I think, last time. Just a convenient terminology in some sense. So, let's take C, just a general category, with a strict initial object. That, of course, denoted by empty. So, a presheaf F on C is before this. So there is this topology. So we denote by the empty, the topology, the coarsest topology, such that the empty family. Yes?
By strict initial object, you mean that it's not the final object? What do you mean by strict?
Oh, strict mean that whenever you have a map from X to empty, then it's an isomorphism. Okay? Okay, so take the coarsest topology such that the empty family is a cover of the empty object. Okay. So I think we have seen this last time. So in particular, the T empty sheaf is a pre-sheaf F such that the value at the empty is the final object. And there is, so we have this inclusion O T empty. I mean, in general, for any topology, the obvious inclusion of the category of sheaves to pre-sheaves. And in this particular case, this has so it always has the left adjoint, yeah, but which is associated sheaf, but here it also has a right adjoint. Which are denoted by BT empty, given by, so if you apply this BT empty to a pre-sheaf, so pre-sheaf F, and then you evaluate at an object Q, then this is equal to the fiber product FU times F empty final object. And yeah, and also the associated sheaf is very simple to describe. It's just you take your pre-sheaf and you replace the value at empty by the final object. Okay. So. All right, so here's the first fact, which is not so not so interesting, but yeah, it's so we assume that XF is diffuse, and I pre-special. So then the claim is that, and again, let's maybe remind you that the topology is no, I have to take it. Yeah. I mean the standard one. Okay, so mean that it's either sinus David psi et al. And so on. Okay, so the claim is that the functor Euler star from sheaf for the empty topology on smooth foliation Fz with any coefficient, I mean, maybe lambda, and you have to take complexes to the same thing on X. So this guy is a left colon functor with respect to the tau local to the injective tau local or A1 tau local model structure. Okay, so this is slightly surprising because usually, I mean, this is also, of course, a right equivalent functor, but then it's for the projective model structure. So yeah, I'm claiming that it is also a left equivalent functor. All right, so here's proof of this. So the fact that first we remark that Euler star has indeed a right adjoint. I upper shake, which is actually given, I think it's given by this. I mean right, where this guy is the right adjoint, right, of Euler star on pre-sheaves. I mean, yeah, I would be if I would work maybe with more general sheaves, then probably this is it's not true anymore that this right adjoint exists. I mean, I think so. So it does have a right adjoint. Also, it's preserve cofibration. This is clear because the cofibrations for the injective model structure are just inclusion, so there's nothing to check. But cofibration, it also preserves quasi-isomorphism. Again, this is clear. So all these facts can be somehow resumed by saying that Euler star is left equivalent for the injective a global structure. So global in the sense that it's without topology. But this is good because then if you want to check if you want to prove this proposition, we only need to check that. So we are left to check. We are left to check that Euler star preserve the tau local equivalences, and so in this case, and sends something. So Euler star of AT empty set of maybe A1, 0, insert something to a contractor to A1 contractible. object, which is actually an easy thing to do. So this part is easy, and I leave it to you. Okay, so at the end we are left to check that our star preserve local equivalences for the topology. And so it's not difficult to realize that this property of that the property that Euler star preserves to local equivalence would follow from the following lemma. So on T empty zero sheaves, the natural map or transformation from, so I think the associated tau sheaf to Euler star, which goes to Euler star associated tau sheaf, is an isomorphism. Right, so this lemma is saying that the functor Euler star commute with sheafification, and it's really easy from this to show what you want. So let me explain why this is true. So proof. Again, just maybe sketch the argument. So so what's behind this kind of statement? I mean, one has to go back to the definition of the associated sheaf, and so one sees that such a statement would follow from the following property. So we need to show that given x prime, f prime in smooth for fx, and a tau cover of z prime f prime, and of course z prime is the base change of z, and a tau cover, then it can be refined. Then it can be defined from a tau cover of x of x prime. Okay, so here's the picture. We have x prime, we have our z prime, we have a cover of z prime, and we want to show that we can refine this cover of z prime by something which is a cover of x prime and pulling back. Okay, if we have such a statement, then we go back to the definition of the associated sheaf, and it's not difficult to see that this implies what you want. Okay, and so I just explained to you why this is true, why we can refine this, and in fact this is yeah. So and maybe before sketching the argument here, maybe I tell you that in fact this is where we need to work with this weird sheaf. I mean, the reason why I speak about T0 sheaves is because actually this is not true in general. There is one stupid case where this phase, this is the case where Z prime is empty. Right? So if Z prime is empty, this fails. But this is the only case, and so yeah, okay. All right. And now, so the general case follows like this. So this problem or this question is local on x on x prime. I mean, I can assume x to be x prime. Okay, so it's local on x for the tautology. In the sense that I can replace my xf by any cover and work locally also. And so in particular, two things follow. So first, we may assume x reduced. And this is because x was diff smooth. And I know that so x reduced going to x will be diff et al. And this is a cover by definition of any of the topologies that I'm considering. Okay. So remember, these kind of things are covers. If xf is diff smooth, so x can be reduced. Now x reduced by closed immersion becomes special, and I have this particular cover. Maybe assuming x is to be affine. So we have this cover. Okay, so and then I have to work either here or here, and if I work here, I get the inclusion of the empty scheme, which I already treated. So I need to deal with that, but that we know is also of the form Z double bracket T. And so in particular, it has a map, it has a retraction. So in particular, the inclusion has a retraction, and then you can use this retraction to pull up any cover of Z. Okay, this is essentially the idea. All right, so. Okay, as a consequence of this, maybe I should write it here. So this is good for us because then we don't need to worry about deriving I lower star. So then I lower star is exact and do not need to be derived. Does not need to be derived. At least if we work with T empty set sheaves. All right, so now maybe I can start the proof of the localization theorem. So yeah, we do the following. So let K be complex pre-sheaves on smooth foliation. So we consider the following. So we have we have commutative square. Let's follow. So we have G our sharp, which is just extension by 0 of the so G again is a open immersion complement to E. That goes to K. That goes to I lower star I upper star K. So sorry, it's a complex of T0 sheaves. So we have this commutative square, and it is commutative because because of this condition. If it's not a T0 sheaf, then this will not commute, and the reason why this commute is because any map of T empty set sheaves from G lower sharp to I lower star is 0. Why is this? Because it corresponds to a map from something to G upper star I lower star, which is empty. I mean, so the point is that G upper star I lower star of a T empty sheaf is 0. This is what makes this commutative. All right, so we have this commutative square, and the theorem is that, so assuming K to be projectively cofibrant, then this square is homotopy co-Cartesian in for the effective, and it's over XF. Okay, so I want to sketch the proof of this, and it is really essentially the original proof of the same thing for varieties, which is due to Morel and Voevodsky. So here's a sketch. So one reduces to the case K of the form X prime F prime tensor lambda for some X prime F prime diff smooth over XF. And in this case, by some easy manipulation, one can somehow not really rewrite, but maybe reduce to consider a slightly different square, which is the following. So I think G, yeah. So it will be U prime. So maybe I don't write the foliation anymore. X prime U tensor lambda I lower star C prime tensor lambda. So it's enough to deal with this square. Okay, so I think the point is that this is the same. I mean, this line is the same thing as there, and here, if you mod out this by this, you get the square below. All right. So, and in fact, we will, yeah, maybe take some place. And in fact, yeah, then we are reduced to consider then, so then enough to show that I think this guy here, tensor with lambda, is an A1 tau local equivalence. And so I should maybe stress here that these guys here are pre-sheaf offsets. Okay, so I have a map of pre-sheaf offsets that I tensor with lambda. All right. So and to do this, I use a criterion. So we have following criterion. So whenever you take BA amorphism of pre-sheaves of sets on some site, maybe foliation, let's say. Then B tensor lambda to A tensor lambda is an A1 tau local equivalence if, in some sense, if the fibers are contractible. Maybe I write it like this: if the fibers are contractible, and more precisely, this means that for every section, so for every A, a section on some y, maybe y over g, so some object of the site of smooth foliation over xf. So for every such A, so we can look at the fiber. Right, so this is now a morphism of pre-sheaf offset from the fiber to the point, but it lives on smooth foliation over y. So this map induces an A1 tau equivalence, local equivalence, when tensoring with lambda. Okay, so and we will use this criterion, and so and we apply this to this morphism of pre-sheaf offset from this guy to this guy. Yes?
I don't actually see how we can move from this one. I mean, we have a zero there.
From here to there? Yeah? Oh, sorry, what?
So there we have zero, and then something.
Yeah, yeah, but so the point is that if you mod out this by this, you get 0 here, and then you get this guy there. Okay, I mean, one should maybe note that this guy here is the final pre-sheaf. I mean, this is like a point, right? Because we are working over scheme, over foliation, over x. So this is it always has value as a point, except so either point or empty. Okay, so this is yeah. Okay, so we apply this criterion to the situation at hand, and in fact, we only need to take sections. Yeah, I mean, I'll do this. Okay, so should I erase this? It seems to it's working from here.
It's working, but it's not recording anymore. So I fear that it's gonna stop. I will check.
Okay. Yeah. So I apply this criterion to this map. For simplicity, I consider sections not from a general y over g, but just from x over f. Okay, so let's fix a section of I lower star z prime over x, which means that, so what is this? This is simply, by definition, this is a map. I mean, it's a section, a real section of z prime to z. Okay, so yeah, that's why I fix it. It's a section, if you want. Yeah, this is equivalent, in fact, to give a map S from z to x prime as xf foliations. Right, so it's a partial, if you want, it's a partial section defined over the closed subscheme Z. Is this clear? Right, so I fix this, and then so the fiber has the following description. So I denote this by T x prime S. So whenever I have an x prime over x and a section, I can define this presheaf, which will be which will be the fiber at the section S. And so this has the following description. So there are two cases. So the value, let's see, the value at P is given by, so there are two possibilities. So either you take maps from over X from P to X prime, but not all of them. You want maps which restrict over PZ, over the fiber of P at Z to the section that we have fixed. Namely, we take a fiber product so PZ, maybe this. Okay, so here there is a particular element here, which is the section S. Okay, you project to Z, and then you and you want to take the fiber product like this. So this is in the case. So if P times XZ is non-empty, and otherwise you take the point. Right, so this is the description of the fiber. And so we are left to show the following proposition. T x prime S tensor is lambda to lambda constant is an A1 Sinisnevich equivalence, local equivalence. All right. So I try to sketch the proof of this. So here's one observation. So first observation, the question is local. Is local on X for the CFT, Sinisnevich topology. So it's kind of clear because we are working locally for this topology. But this has the effect that we may assume that XF is something like this. So we can reduce to this case. So it's the same argument as before. So first you assume that x is reduced, and then you use the fact that you have this cover by the completion and the complement. And on the complement, there is nothing which is happening, so you have to deal with this case. So the second observation, which is somehow this is maybe the main observation here, is that so if you have the following assume that we have the following commutative triangle. So we have x double prime going to x prime, and so it's going to x. Everything is going to x, and here we have something which is diff et al. And we also have these partial sections which are fixed. Right, so assume that we are in this situation. So these are the sections. This is a closed immersion. So the second observation is that the map, so there's an induced map like this, is an isomorphism after simplification. I should probably stop soon. Maybe just finish this proof. All right. So, yeah, we want to show that this is induces an. So what does it mean? It means that if I give myself p, which is diff smooth over x. I want to show that, that locally on P the map. So I want to show that locally on P the map is an isomorphism. But then locally at P, this means that again it's the same story. So I could I have these covers, so I can assume that P, so we may assume P reduced, and then we have this cover Pz and P minus Z, and so at the end we are left to show that, so left to show that T x prime S prime of something like, so maybe I call Q, this is P times xz. So we are reduced to show that this map is a bijection. And this is, this is kind of clear. It's so this somehow this follows somehow from the Taylor expansion. So essentially, a map, any map from Q, to x prime or x double prime. No, sorry, any. Right. So the point is that if I fix a map like this, so if this is fixed, sorry, this is T. Then there is exactly one extension like this. Okay, because this is diff eta. And this is an argument. I mean, you can see this using the Taylor expansion, because any morphism from this to this, which is diff eta over here, is given by a Taylor expansion. Okay, so it's an easy argument like this that you. All right, so I think I should stop now. Okay, because there is the colloquium and my phone is ringing also. Sorry.